Okay, good morning. Welcome to the morning session. So it is a great honor for me to introduce Nikolai Reshetikhin from the University of California, Berkeley. Kolya received his doctoral degree in 1984 from the Steklov Institute in Leningrad, where he was one of the main actors in the development of the quantum inverse scattering method, which led to the construction and definition of quantum groups, which is now one of the main topics in representation theory. So Kolya obtained several important results and also provided deep insights and innovative ideas in a number of areas of mathematics and mathematical physics, including low-dimensional topology, representation theory, statistical mechanics, quantum field theory. So among his results, I will quote the famous Reshetikhin-Turaev invariant of three manifolds, which is a mathematical version of the Chern-Simons invariants introduced by Witten. And several tools in the representation theory of quantum groups, such as Q characters, the Kirillov-Reshetikhin modules, and his many results on limit shapes, in particular for dimer models and six-vertex models, and the Batalin-Vilkovitsky quantization on manifolds with boundary. So he was a plenary speaker at the International Congress of Mathematics in 2010 in Hyderabad. Hi, Kolya. I'm supposed to virtually give you a medal. I will show it, and you will receive it. So this is a medal for plenary speakers at this Congress. Okay, so the talk will be on Functorial approach to harmonic analysis on quantum groups, quantum modular spaces, and superintegrable systems. So please, Kolya.
Thank you, Giovanni, for a very generous introduction. So I should start sharing the screen, I guess.
Very good.
Okay. So, so this is the original title of the talk, and one of the main subjects is quantization, and quantization can be regarded as deformation. So I was following the tradition of the deformation, and I deformed my presentation again and again. And what you see now is the n plus first iteration in this one parametric family. So here is the...
Oh, yeah, okay, perfect.
Yes?
Perfect. No, there was some small technical problem here on our side, but now it's all okay. So please continue. Sorry.
Mm-hmm. So here's the big picture. This is what I will be talking about. The construction of superintegrable systems on modular spaces of flat connections. Then I'll use topological quantum field theory to quantize these systems. And essentially, this will be based on the representation theory of quantized universal enveloping algebras when Q is a root of unity. This construction can be pushed to the generic values of Q. And this is really where the harmonic analysis starts. So here I should emphasize that this part about harmonic analysis probably will not fit in this talk, but it's a very interesting development based on joint work with Jasper Stockman and also in other part with Hadewig de Klerk and Jasper Stockman. So this is the big picture for this talk, which could be a little bit technical for such occasion. So the plan is the following. I'll introduce the notion of, and I will remind the notion of superintegrable Hamiltonian systems. This is an important generalization of, I want to call it generalization, although there are different opinions. Generalization of Louisville integrability. And so then I'll introduce the family of superintegrable systems on modular spaces of flat connections on the trivial G bundle over a surface. Then I will describe the quantization based on the topological quantum field theory, which Giovanni already mentioned. And then I'll mention some remarkable facts and open problems. And so as a result of the deformation of the original title and original idea of this presentation, here is what the running title is: Quantization of superintegrable systems on modular spaces of flat connections and topological quantum field theory, more precisely quantum Chern-Simons. So this is based on joint work with Semyon Artamonov, Hadvig de Klerk, and Jasper Stockman. So first, what are superintegrable systems? They have several names. So superintegrable system is the latest name for them, which stuck, and it's probably most. Okay, so the other names are degenerate integrability, non-commutative integrability, and so on. So the story goes back to Pauli, Smorodinsky, Fogg, Winternitz, Nikhoroshev, Mishchenko, and Fomenko. All these people contributed to the subject. So let me give the definition. So yeah. So let M be a symplectic manifold, A be the algebra of smooth functions on the symplectic manifold, H be some Hamiltonian, and by ZHA, I will denote the centralizer of H in A. So we will say that Hamiltonian flow generated by H is superintegrable if there exists subalgebra in our algebra of classical observables, such that the rank of this subalgebra is 2n minus k. That means that there exists 2n minus k elements which form a maximal independent set. So it's in algebra, it's also known as Krull dimension. If our subalgebra is the algebra of functions on some manifold, that's the dimension of this manifold. And this is the type. This is supposed to be J, this instead of this Z. So, so this is the first part of the definition, and then the Poisson center of J should have rank K. In other words, it should have it should contain maximal K independent functions, I1, Ik, and the Hamiltonian should be also in the center of this algebra J. So this is a superintegrable system. And algebraically, you can see that the main ingredient is a collection of, it's an algebra of functions on the phase space, that's A, the Poisson subalgebra J, and the center of this, the Poisson center of this Poisson subalgebra I. So such that the rank of the center should be K, the rank of this Poisson subalgebra J should be 2n minus k, and the rank of our classical observables is 2n. So you see that it's very important to have this balance of dimensions. So typically, if you have a Poisson commutative subalgebra in A, its centralizer, which is J in our case, will have smaller dimension. So, so this is the superintegrability algebraically. Geometrically, it means the following. Our symplectic manifold is equipped with these two projections. First projection projected to a Poisson manifold of dimension 2n minus k. And the second projection projects this Poisson manifold to a k-dimensional manifold with the trivial Poisson structure, such that fibers are 2n minus 2k dimensional symplectic leaves. And when I say fibers, I always mean generic fibers. So the generic fibers of the projection P1 will be k-dimensional isotropic submanifolds. And you can see that this picture, when k is equal to n, P and B collapse together, and it just becomes the Lagrangian fibration where generic fibers are maximal isotropic submanifolds, in other words, Lagrangian submanifolds, and that's the case of the Louisville integrability. So when k is equal to n, that's a Louisville integrable system. Now, what can we say about superintegrable systems? There is this beautiful theorem due to Nikolai, who at some point was a student of Arnold. The theorem says the following. Flow lines of our, if we choose these k-independent elements in the Poisson commutative subalgebra I, they generate affine coordinates phi1, phi k on level surfaces of the integrals of motion j1, j2n minus k. In other words, on fibers of P1. So the action angle variables theorem also exists here. It says that in the neighborhood of this fiber, the symplectic form can be written in this canonical form as it would be for the Louisville integrable systems, but there is a correction, so we don't have enough action angle variables to have Darboux coordinates on M. So there is an extra piece, and that's the symplectic form from the symplectic leaves of P. So it's a symplectic form over here. And then each connected component of P1 inverse of the isotropic submanifold upstairs is isomorphic as in the usual Louisville theorem, copy of Rn and a torus, so that the total dimension is k. Flow lines of any Hamiltonian from our subalgebra I of Hamiltonians, flow lines are linear in this affine coordinate system. And so this theorem generalizes very naturally Louisville theorem for completely integrable systems. So just want to emphasize that there is how the Louisville integrability related to superintegrability. So suppose that we have a Louisville integrable system on our phase space M. So in other words, in the classical algebra of observables, we have the maximal Poisson commutative subalgebra. And here we have, as was explained earlier, we have two subalgebras, the Poisson subalgebra of rank 2n minus k, and its Poisson center of rank k. So we will say that the superintegrable system on the right is a refinement of the Louisville integrable system if this Poisson subalgebra over here, the for superintegrable system, contains the maximal commutative subalgebra in the Louisville integrable system. And this maximal commutative subalgebra contains the center of this Poisson subalgebra. So in this case, we can say that n-dimensional Louisville tori for the Louisville integrable system are actually fibered by k-dimensional Louisville tori of superintegrable system. So we have more information. In the extreme case, when k equals 1, that's the maximal superintegrability. It just means that all trajectories are periodic. They are one-dimensional tori. So here is an illustration of this for four-dimensional phase space. So this is the Louisville integrability. We have our Louisville tori are two-dimensional tori. I assume that they are compact. So it's possible that the system is integrable, but there will be no periodic trajectories. But if it can be defined by a superintegrable system, then we know for sure that all trajectories are periodic, and we can split these torus into one-dimensional flow lines. So the refinement may not exist, but when it exists, it gives more information about our integrable system. So examples of superintegrable systems, when the classical example is the Kepler system, this is when phase space is six-dimensional cotangent bundle to R3. So the Q are coordinates, P are momenta, symplectic structure is standard, the Hamiltonian is just, as usual, P squared over 2 minus gamma over the distance to the origin, and gamma is positive, that's the gravitational constant in the Kepler system. So the superintegrability is given by these projections. So M is R6, the six-dimensional phase space. In the middle, there is a five-dimensional Poisson manifold, and at the end, there is one-dimensional base. Algebraically, this one-dimensional base is the spectrum of the classical Hamiltonian itself, just a set of possible values of the Hamiltonian. And this Poisson, intermediate Poisson subalgebra can be described by, as usual, by angular momenta and length vectors. So in particular, the symplectic leaves of this five-dimensional Poisson manifold, well, they depend on the value of the Hamiltonian. And this is a classical version of the very famous degeneration of the spectrum of the hydrogen atom. So if E is positive, then they are co-adjoint orbits for SO, for the Lorentz group SO31. For the zero energy, this is the cotangent bundle to S2. And for the negative energy, these are co-adjoint orbits for SO4. The other examples are spin calogero Moser Sutherland systems and various sort of chains construct out of them. So, so these are some examples. And then the other examples are relativistic versions of spin calogero Moser Sutherland models and of Ruijsenaars models. And now I want to present a large class of of superintegrable systems on modular spaces of G-flat connections. And I should say that this example that I mentioned, the relativistic versions, it will just be a particular case of what I'm going to talk about. And the second example, these are some kind of degenerations, flattenings of some other examples from this list. So this will be a big list of superintegrable systems, and let me so let me first remind what the modular spaces that I'm going to talk about. So here, G is a connected, simply connected Lie group. G fancy is it's the algebra. So we will, by sigma n, I will denote an oriented compact surface with n components of the boundary. I mean, it's a topological surface, so you can also think about this surface as a surface with n punctures, if you think correctly about the punctures. So mg sigma is the modular space of flat connections. So this is simply you take the space of flat connections on a principal G bundle over sigma, trivial G bundle, and you mod out by the gauge group, which is simply the mappings from sigma to G with no special conditions on the boundary. On the boundary, points are still mapped to the whole G. And it's a simple fact that this modular space is isomorphic to the character variety of the fundamental group. In other words, homomorphisms of pi1 to G mod G. So I'm meeting some details, and I'm not pedantic at certain points, but forgive me. So the beautiful thing about this space is that it's a finite dimensional variety, which has a natural Poisson structure. And that's, that observation is due to Atti and Bott. And there were some developments after the original paper. So symplectic leaves of this Poisson manifold you can obtain by fixing conjugacy classes of holonomies around boundary components. So I will denote the symplectic leaves by this thing. So now there is a nice universal description of the Poisson structure in terms of chord graphs or chord diagrams. So this is the following. We'll say that a chord diagram is a graph that's written on a surface where there are solid lines and dashed lines. These are the chords. And the algebra of chord diagrams, this is simply the span of isotopy classes, of continuous deformations of such graphs on a surface, modulo 4T relations. So these 4T relations, they go back to perturbative theory of quantum Chern-Simons theory. And I think they were first introduced clearly by Dror Bar-Natan in 1995. So it's just you mod out by these relations. And the meaning of these relations is more or less the following. They kind of, if you take the simple algebra G and A is an orthonormal basis with respect to the Killing form in this Lie algebra, then you can construct these elements so-called mixed Casimirs. They satisfy this identity, and this identity is actually what the meaning of the four-term identity. So theorem that goes back to 1996. If you will define the bracket between two chord diagrams by this formula, where you glue this gamma 1 and gamma 2 at every intersection point of gamma 1 and gamma 2 in such a way that you glue a chord between these two graphs. So, and here epsilon p is just an oriented intersection number. So sigma is oriented, it's defined. And this bracket is a Lie algebra bracket structure on this space of chord diagrams, and together with the commutative algebra structure, which is just the formal commutative multiplication, it gives a Poisson algebra structure on the space of chord diagrams. So this structure was introduced first actually by William Goldman in 1986. For the quotient algebra, when you replace the chord by this configuration. and it describes the modular spaces for classical Lie groups. So, then there is an actual class of functions on modular spaces obtained by the evaluation of these chord diagrams. So they are the following. So first, one should fix G coloring of gamma by assigning finite dimensional representations to each edge, and a vector C V, that's the notation here, an invariant vector in the tensor product of the adjacent vector spaces. So I forgot to put here G, symbolizing that it's actually a G invariant vector. And then to chords, we should assign adjoint representation of G. To these trivariant vertices, we assign the structural homomorphism from the Lie algebra to endomorphisms of G, which is an invariant vector in this tensor product. All these tensor products should be replaced by invariant parts of the tensor product. And then a graph function on connections is simply the pairing between the holonomies of a connection along the edges and these invariant vectors at vertices. So this clearly gauge invariant function on the space of connections, and if A is flat, it depends only on the on classes of continuous deformations of gamma. So so in other words, we have a natural mapping from our algebra of chord diagrams to the algebra of functions on the modular space. So the following theorem follows more or less from a T-bot construction immediately, and the corollary is that our algebra of chord diagrams is some kind of universal object for all these modular spaces. So in other words, if we color it, we have a Poisson homomorphism from the colored chord diagrams to the algebra of functions on modular space. Okay, so this graph functions, this is a convenient tool to work with functions on modular spaces. And now let me describe superintegrable systems on this Poisson varieties. So in order to to fix the such superintegrable system, we should fix k non-intersecting, non-self-intersecting curves, such that none of these curves can be deformed to the boundary, to some boundary components of sigma. So here is an example of two curves, such curves, and this is what we shouldn't have. We shouldn't have any of them being deformable to the boundary. So now let's consider Poisson subalgebras. So this is the algebra of functions on our modular space. And J is the algebra of functions, of graph functions, for graphs that do not intersect these fixed curves C1 and CK. And in this subalgebra, we have, so it's a Poisson subalgebra. It doesn't have to be Poisson commutative. But in this subalgebra, we have the subalgebra of graph functions for graphs which are contractible to the disjoint union of these curves. So here is an example of such thing. So we can have some very complicated graph on this band, but this band is contractible to Ci. So this is an example of our graph function. And because such graph functions can be deformed to Ci's, each of them, so they all Poisson commute. They all can be deformed in such a way that there are no intersections. So this is why this subalgebra is obviously commutative. This subalgebra doesn't have to be commutative, and it's not Poisson commutative. And the remarkable fact about these two Poisson subalgebras is that I is the Poisson center of J. And, well, this is the, so in order to have a superintegrable system, we also have to have a balance of dimensions. And in fact, it holds. So the rank of this subalgebra plus rank of this subalgebra is equal to the dimension of our modular space. And this last sentence should be at the end of the part 2 of this theory. So in other words, remarkably, for each such collection of contours, we can have a superintegrable system. And if you remove one of these contours, say if you remove C1 from this collection, the remaining contours C2, Cn, well, they still define some superintegrable system. And actually, this superintegrable system will be a refinement of the superintegrable system with C1. In other words, we can refine those systems to the point where there is only one C left. And that means that, in fact, all these systems are maximally superintegrable. So an example, we can take a torus with n punctures. And when I say punctures, I always mean small holes, meaning the actually the boundary component. So so then there is a natural choice of corresponding contours. We simply place them between the holes, and this natural choice corresponds to variety of these integrable systems. These are generalized spin Calogero-Moser-Sutherland systems. If n equals 1, these are exactly relativistic spin Calogero-Moser-Sutherland systems, Ruijsenaar systems. These are also the systems that were studied by Chalich and Feyron. So it's already in this case, there is a whole zoo of superintegrable systems that has been studied before. And the generations of these systems, they give the spin Calogero-Moser and other similar systems. Okay, so so the main result here is that we have this strange collections of superintegrable systems on the modular spaces. And I just want to, well, so everyone who is interested in integrable systems, we know that there are, on modular spaces, there are so-called Hitchin integrable systems. These are different systems, something else. What's the relation to Hitchin systems? I don't know. So, so now we want to quantize those systems. And first, there is a, let me remind what quantization is. So you see in mathematics, there is quantization. In physics, there is a semi-classical limit. Of course, nature is quantum by definition. We just don't see with the unarmed eye the quantum structure. So from the physical point of view, all these arrows should be in the opposite direction. But it's, you know, mathematically, it just means that these are the deformation arrows. So quantization of a Poisson algebra, usually it's this piece that consists of two parts. First, we want to construct a family of associative algebras which deform this Poisson algebra. That's the deformation quantization philosophy. And second, we want to, I mean, since we have a family of associative algebras, you know, if you are familiar with algebra, the very first question you ask are, what are the representations of this algebra? And so the second kind of task of quantization program is to construct representation spaces, and the usual desire how to construct these representations is through the geometric quantization of symplectic leaves of the underlying Poisson manifold. In many cases, it's very difficult to construct both. More precisely, all three components: the associative algebra, the geometric quantization spaces, and the action of the algebra on these spaces. But fortunately, in some cases, it can be done. So our friends, our examples are exactly of this kind. And so first, let me describe some extremely natural object, the kind of universal quantization of this universal Poisson algebra of chord diagrams on sigma. There is nothing easier than this. So it's an algebraic quantization of this Poisson algebra. And this is an associative algebra, which is simply the span of isotopic classes of ribbon graphs in the three-dimensional manifold, which is a three-dimensional cylinder, sigma across an interval. Since everything is topological, this interval, I'll refer it sometimes to as a unit interval, but in fact, it's just a topological interval. So associative algebra structure is very simple. So we take two such tangled graphs, gamma 1 and gamma 2, and we move gamma 1 a little bit to the top of this cylinder, gamma 2 to the bottom of this cylinder, and so that they are sufficiently separated in the vertical direction, and that's the product. And it's obvious that it's associative, and it's also clear that it's not necessarily commutative. Gamma 1 composition with gamma 2 is not necessarily equal to gamma 2, gamma 1. So here's an example. If sigma is a torus, so torus is like a donut, and I slice the donut, as many people do in the morning, kind of along the direction of the donut. So this is what is written here. So this is an example of gamma in T1 across an interval with one puncture, and that's another gamma, and that's the composition. So this algebra has a natural filtration by the subspaces where you apply this operation nabla V to a vertex V, and it produces this difference, undercrossing minus overcrossing. So, so the A0 is A itself. This is the filtration with this nice property. And so you can see that the associated graded algebra of this filtered space has a natural Poisson structure. The commutative multiplication comes from here, and the Poisson bracket comes from here. And this associated graded is naturally isomorphic to the algebra of chord diagrams. This is where chord diagrams naturally appear. So this the class of this element goes to the two components connected by the chord. Okay, so this is some kind of version of a deformation quantization where filtration replaces the degrees of H. Usually the deformation quantization is given as a deformation family with H, and as H goes to 0, it converges to its classical version. So here, these degrees of H are replaced by the filtration. So, so this algebra also comes with a universal representation space, which is simply the span of isotopic classes of ribbon graphs in the handle body of sigma. So in other words, take sigma. Well, strictly speaking, one should standardize it in a certain way so that we know how to fill it with water and fill it with water. This is our handle body, and it's a three-dimensional manifold with the boundary sigma. And the action of A on V is just gluing the graphs from the cylinder to the, taking disjoint union of graphs from the cylinder with disjoint union of graphs in the handle body and gluing the cylinder to the handle body. Again, when it's a torus, it works like this. So this is a graph in the cylinder. This is a graph in the handle body. And when we glue a cylinder to the handle body, we have the action of gamma on gamma prime. So we have the universal quantization of these chord diagrams. We have the universal representation space of this universal quantization. So now somehow we have to do something similar with this quantization to what we did with the universal algebra of chord diagrams. We have to evaluate it using the information from the Lie algebra G. In the case of chords, these were the graph functions. And in the case of quantum, in this quantum setting, when we have the algebra A and the representation space V, we will use the topological quantum field theory to evaluate this algebra and this vector space to a quantization of the modular space and superintegrable systems. So the main goal of this discussion is not a quantization of the modular space. That has been done a long time ago. The main goal is the quantization of superintegrable systems. So there is something else that one can say about quantization of modular spaces. I'll mention it at the end. There is another approach to this problem based on quantum groups and Poisson-Lie groups. So that's on the classical level, these are so-called Fock-Rossley Poisson structures. On the quantum level, this is the work of Alexeyev, Shumeros, Grosse and Shumeros. And I'll mention it at the end. So, now, what is a quantization of a superintegrable system? So first we have to fix quantization of our algebra of classical observables. And then here is some kind of quasi-definition. So quantization of the superintegrable system given by this triple is a triple consisting of the quantization of our algebra of classical algebra of observables. That's the A. Quantization of J, of the Poisson algebra J, and the quantization deformation of the Poisson commutative algebra I. So I hat can differ from I only in the way how commutative algebras can be deformed. And what we should have is that this I hat should be the center of this algebra A. And in the appropriate sense, J hat should converge to J and I hat should converge to I as H goes to 0, but this is already separate. This should be quantizations. So the most difficult, I mean, if you really want to have a clean definition, the most difficult part is to say what the balance of dimensions are. So for this, we have to replace crude dimensions by the corresponding notions for non-commutative algebras. So I want to spare the details now, just just a remark along these lines that say a typical kind of most essential difference between quantum superintegrable systems and quantum Louisville integrable systems is in the structure of the joint spectrum of this commutative subalgebra I have. If it's a Louisville integrable system, the multiplicity of the spectrum typically is simple, either simple or stable. Say the eigenvalues can be double degenerate or n times degenerate, and this n is fixed. It doesn't depend. It remains fixed as h goes to 0. A typical feature of the superintegrable system is the following. The multiplicity of this spectral point C behaves as h goes to 0 as h to the minus n minus k. This is actually half of the dimension of the symplectic leaf over this point C in the classical setting, times the symplectic volume of this symplectic leaf. So this is a kind of a typical asymptotical dimensions of such spaces in the geometric quantization setting. So, and that's exactly what happens in the hydrogen atom. We all know this. As h goes to 0, if you fix the energy level, then the degeneracy of this energy level will behave as h to the minus 2. So these are hugely degenerate quantum systems, and this is why the name quantum superintegrable system or degenerate quantum integrable systems, they're kind of synonyms. Okay, so this is what we want to do for the superintegrable systems on modular spaces that we discussed earlier. We want to construct the quantum counterparts. Okay, so we will use the topological quantum field theory quantization of these modular spaces to construct quantum superintegrable systems. So the concept of three-dimensional TQFT is just a functor from three cobordisms to vector spaces, roughly speaking. It maps surfaces to vector spaces and three manifolds with possibly with some ribbon graphs in them. It maps to vectors in the vector spaces corresponding to the boundaries of these three-dimensional manifolds. So this is an old story, by now relatively well known. So an example of quantized universal developing algebra is just the associative algebra generated by three elements E, F, and K with these defining relations. If Q is this root of unity, for some technical reasons, I assume that L is odd. And of course, I assume that M over L is, M and L are relatively prime. So in this case, one can define a small quantum group. That's the finite dimensional Hopf algebra. That's the quotient of this algebra over this extra ideal, which fixes K to the 2L by 1 and E to the L and F to the L by 0. So basically, this is the kind of algebra that we used with derive in this paper. So, I will return and I will mention again the role of the path integral quantization. It's kind of still a remarkable open problem to prove that one is equal to the other. So the construction of this combinatorial TQFT is the following. First, for some technical reasons, we should use some kind of standardization of sigmas. So here's an example of such choice. On the left, when we have no punctures, on the right, when we have punctures. So such standardized surface is mapped to a vector space, which is known as Verlinde vector space. And it can be characterized as simply as a combinatorially, it can be characterized as a vector space with the basis, which is parameterized by colorings of this standardizing graph by irreducible representations of small uq and by the corresponding invariant vectors. The vector that corresponds to, that's actually the invariant of three manifolds. I will not give the definition of this. It's essentially, the whole idea is based on the representation of three-dimensional manifold M as a surgery along some collection of links. And so the components of this vector tau in this standard basis can be described as certain special invariants of links in S3 that satisfy certain special relations. So it's technical, so I'll skip this, but that's in a nutshell, this is the idea. So we have Verlinde spaces associated to surfaces, and we have these vectors associated to three-dimensional manifolds. So if you choose a different standardization, you will have different bases. So you have this description of the kind of space that's isomorphic to this one. There is more geometric description of Verlinde spaces in terms of geometric quantization. So that's okay. So very good. So that's about this standardization. Now I cannot make this remark. So there is actually a big difference between various choices of these roots of unity. So if you choose Q to be a primitive root of unity, then this is really a quantization of the Chern-Simons theory. So what's expected is that these combinatorial invariances L go to infinity, they go to Witten's path integral perturbative quantization, but it's still a big conjecture, and the main obstacle is the kind of this clean definition of the perturbative path integral for manifolds with boundary. So this was a big motivation for the series of papers with Alberto Catania and Pavel Myov on the BV-BFV quantization. This was one of the strongest motivations for this development. But what's remarkable is that if you choose a different root of unity, for example, M equals 2, then there is no semi-classical behavior as you would expect from Chern-Simons. There is no oscillatory contributions. There is something that's typical for the volume conjecture. That was found by Cheng and Yang. And there are some arguments that goes back to Gukov's paper on complex Chern-Simons that it's very natural in this case to expect that it's a complex Chern-Simons theory. So kind of a big question, what happens if L goes to infinity, M goes to infinity such that Q is fixed? It's probably related to this Gappa-Kumar-Waffa invariance. But again, this is a question. So, Giovanni, how much time do I have?
Maybe if you...
I'm worried about this.
Like 4 minutes, so we have time for questions.
Okay, thank you. Okay, so now quantization of the superintegrable systems. So here is the recipe. We replace the coadjoint orbits according to the tradition of the quantization of coadjoint orbits. So we replace the conjugacy class in C that defines the modular space by a highest weight vector of an irreducible UQG module. So then we define this algebra as the evaluation of graphs in sigma across an interval via the TQFT functor that we have on previous pages. So it's simply the span of toes, and according to the to what it should be, these are the vectors in V tensor V dual, which is the endomorphisms of V, and then J will be the span of toes such that the projection of gamma to sigma does not intersect these curves C1, Cn. And I is the subalgebra generated by toes for the liftings of Ci to the cylinder. So it's very similar to the way how they are defined in the classical case. But instead of the graph functions, we use the TQFT functor. This is why there was a title Functorial. There was the word Functorial in the original title. So now an example. If it's a torus with n punctures, then the Verlinde space is this. So, but when we have a torus, we always have a complementary torus in S3. So this means that there is a natural scalar product where we pair the Verlinde space corresponding to the torus with the Verlinde space corresponding to the complementary torus. So the pairing between the elements of the basis is given by this invariance of these graphs in S3. These are the numbers. An example, if n equals 0, this is the so-called S matrix that is kind of a big thing in conformal field theory. So if, okay. So, so the matrix elements of tau of gamma, when gamma is a graph in a cylinder, again, this is just the invariant of this tangle, where you tangle gamma to the the result of the gluing of these two skeletons, the skeleton corresponding to E and the skeleton corresponding to this E. Again, this is a number which is the invariant of this tangled graph in S3. So one of the corollaries is that if you will take any contour C colored by representation W, it acts diagonally on this basis. So in other words, this basis is the basis of eigenfunctions for our commutative subalgebra. And now I came to the most interesting part, and this is where I have to finish. So I hope that this will just give you kind of food for thoughts. So I have to say something about harmonic analysis now. So these functions, these are exactly finite dimensional conversions of the Ettingov-Farchenko trace functions, which appear in the context of dynamical R matrices, McDonald operators, and QKCB equations. So the beautiful fact is that in this particular case, when we have cylinders and Verlinde spaces, we don't have to worry about roots of unity. This whole thing can be extended to generic Q. The non-trivial part is that now the representations that run along these circles, lambda and U, they can be replaced from finite dimensional modules to Verma modules. And maybe even more interesting, maybe to principal series representations. So when you replace it to Verma modules, that's something that is defined, and that's the case of the Ettingov-Farchenko trace functions. And this is a joint work with Hadley de Klerk and Jasper Stockman. So then the relation to the combinatorial quantization of modular spaces. That's, I have no time to mention, unfortunately, that's a beautiful subject. So the extension to Cosmodi algebras, yes, you can extend these constructions to the case when these are the modular spaces for Cosmodi algebras, and instead of the trace functions for finite dimensional case, as here, we'll have trace functions for affine Cosmodi affine algebra case. So the most interesting situation is that there are other modular spaces. You can impose boundary conditions, non-trivial boundary conditions on gauge transformations. For example, if you will say that we quotient not by the whole gauge group, but by a smaller gauge group, which has such that the gauge transformations are in the Borel subgroup of G on the boundary. So then we will have this for Goncharov modular spaces. And the beautiful thing about these modular spaces is that they have cluster algebras. So similarly to this, we can choose a maximal compact subgroup, and we can again consider the gauge group where the boundary values of gauge transformations are in the compact subgroup. So this is related to boundary QKZB and to all these stories. So this is an ongoing work with these two people. So then there are many interesting questions about semi-classical limits, n goes to infinity limits, and so on. So, sorry, I should have organized the talk better. I didn't have time to talk about most interesting things. Thank you.
Thank you for this nice talk. Thanks for this inspiring talk. Are there questions? Yes.
Thanks for the talk. I have a question that you proved that the associated gradient of the A is isomorphic to the chord diagram algebras. Whether this algebra itself is isomorphic to the chord diagram algebras, not the associated gradient.
That I don't know. I mean, I just don't want to give some kind of silly answer. I think it's an open question.
Okay, thank you.
Yes.
You can filter through. You can consider homomorphism from the algebra of things to kind of formal. Anyway, so the answer to your question is probably not.
Okay.
Or rather, the question is I don't know. The answer is I don't know.
Hi, Kola. Thank you for a nice talk. So you mentioned several schemes of quantizing the moduli of flat connections, and you probably know there is this more recent scheme using factorization homology, whatever it is. But one feature of it is functorial in terms of the surface. And since your superintegrable systems are defined in terms of sets of non-intersecting simple closed curves, right? One may wonder whether it would allow also a very natural quantization in terms of factorization homology, because your systems are so geometric and their functoriality seems to be, I don't know that theory very well, but functoriality seems to be automatic. I don't know whether you or your collaborators thought about it, but that seems to be a natural direction. Thank you.
Thank you, Anton. I agree. You know, I should have learned by now this factorization homology, but I still didn't master it, so I cannot say whether it works or not. I completely agree that this is something to look at.
More questions? Yes.
All right, so I'm not used to this abstract definition of topological quantum field theories, so I wonder what this means. But still, I am used to something like mathematical gauge theory, so like Wilton-Loops, for instance. So on one slide, you defined the topological quantum field theory to be a map from let me see again, I think 3 cobordisms to vector fields. So can I think can I think of those surfaces or 3 cobordisms as something like the loops you have in mathematical gauge theory and what it maps to, like the Wilson loop observables, or is it something different?
No, that's so when I say that it's possible, it's possible to have these tangled graphs in M, these are the Wilson loops, or rather Wilson graphs. You can attach the holonomies, you can attach edges to some kind of invariant vectors. Yes.
All right,
so this
thanks
is,
a lot.
You can think of this as some kind of combinatorial quantization of Wilson graphs.
Mm-hmm. More questions? So maybe I have a quick question. So what is your expectation? Will we have soon some Reshetikhin to Raev invariants where Q is not a root of unity?
I wish. Actually, I don't think it's so easy. It's just in some very special cases it's possible, but not for all manifolds. Also, you reminded me that there is another natural question. There are other TQFTs. For example, there is this beautiful construction due to Anderson and Kashaev of TQFTs related to the to Teichmüller spaces, quantization of Teichmüller spaces. So I do expect that there is a counterpart of what we did in this setting.